Hello everyone, I'll be presenting on how to go from a neural network module to FPGA hardware. This is interesting because there's, as pointed by Eric Kolu, there's an increasing launch of nanosatellites, and this means an increasing interest in science on space. But this science generates a larger amount of data, and we cannot transfer all this data down to Earth. So maybe we need to select a downlink, maybe we need to compress it. But something needs to be done with this data. And neural network can be used for this purpose. However, we cannot run neural networks on commercial off-the-shelf CPUs or GPUs. Those are not suitable for radiation environments or for use in space. So one solution is to run them on FPGAs. And for that, we can design custom accelerators for neural networks and implement them on FPGAs. A little bit of background. So AI in space can be used for autonomous navigation, Earth observation, remote sensing, science with planetary exploration. We can perform science on site. We can detect anomalies in space. A neural network is a subset of machine learning, which machine learning is a subset of AI. And a neural network is comprised of an input, hidden layers, and then it has its output. Those neural networks can be convolution neural networks, can be spiking neural networks, can be binary neural networks, and they can be used for pattern recognition, classification, data reduction, etc. So reconfigurable FPGAs belong to the reconfigurable hardware category. And reconfigurable hardware is when you have different blocks, which each block is either a lookup table, DSP, and then you configure the connections between them to perform Boolean logic. These FPGAs allow flexibility because you can accelerate the algorithms in FPGA, then you can change those algorithms and when they're already in space. Contrary to, for example, ASICs, where you design the hardware, you accelerate something, but then you cannot change it. They offer higher performance than CPUs, and there are radiation hardened by design FPGAs, which are suitable for space. And if you design an accelerator for an FPGA, is be portable for radiation hardened FPGA. So just so you have an idea, the board with which we work in my group with which I work is the ZCU 104 from Xilinx. The FPGA itself is the chip in the middle. The rest is the board that contains various peripherals. And when we design an FPGA neural network accelerator, those neural network accelerators normally follow two patterns. One pattern is a data flow accelerator, and the other is a time multiplex accelerator. The data flow accelerator maps each layer of the neural network onto the FPGA fabric. So each layer is its own hardware, while the time multiplex accelerator has different processing elements, and each layer is executed in the same processing elements, and then it goes to the next layer and passes through the same processing elements until the inference is done. Me and Arthur conducted a survey, and we analyzed all the state-of-the-art of use cases implemented. So use cases that leverage neural networks and were implemented in FPGAs. Most of these use cases were performing classification tasks. Most of them were convolution neural networks. And most of those use cases performed offline learning, which means that the training process was done on Earth, and it was supervised. So it needed prior data. Very few did onboard unsupervised, which should mean onboard unsupervised would be when you have a neural network that is learning new patterns in space. That could be very interesting. The size and the energy consumption of the use cases that we studied didn't exceed the 50 million parameters. So the maximum, the biggest neural network that has been implemented for space had a little bit less than 50 million parameters. And the energy consumption depended not only on the number of parameters, but also didn't spend only on the number of operations, but also on the depended on the inference time and the power consumption. The inference time is influenced by the number of operations, and the memory footprint of the neural networks is influenced by the number of parameters, of course, but also by the quantization approach, because most implementations quantized their neural network, and this means instead of executing floating point operations in space, they used fixed point precision, which is like computing integer, so multiplications and operations. One surprising fact is that most of these applications did not consider radiation, did not even address radiation hazards. Only a few mentioned them, and even fewer implemented some kind of technique to mitigate them. Mitigation techniques in hardware can cost hardware and can influence the accelerator. So this is a lack of research. In our work, we implemented 4 use cases. We accelerated 4 use cases in the FPGA. We accelerated the variation autoencoder, only the encoder part, and this compresses the data from by a ratio of 16,000 or so. And we accelerated the MMS neural networks, the CNET plus Scholar, and the Spectra. The variation autoencoder is comprised mostly of convolutional layers, and its input is a 2D image, RGB image. The CNET plus Scholar input is like a grayscale image, and this neural network is also comprised mostly of convolutional layers, followed by activation layers and pooling layers. Esperto was the simplest model of all of this, and is it's 6 perceptrons in parallel, followed by a sigmoid and a greater than layer. And the MMS neural networks included the logistic net, which was the smallest, and these neural networks perform classification of MMS on the MMS data. And those are also convolutional neural networks, but they operate on 3-dimensional data. As you can see, all these use cases have had a very different number of parameters and number of operations, and we use 2 methods to accelerate them. We used VTZai, which is a predefined accelerator that you program the FPGA with this accelerator, and then you compile the models to instructions that the accelerator understands in a random. And VTZHLS, which we first transform the models into a C program, and then we transform this C program into hardware. And with the VTZHLS, we obtain one like a data flow accelerator, as I mentioned in the beginning in the background. in terms of performance, we observed that with VT's AI, we could achieve very good results in terms of speed up. The power consumption of VT's AI on the ZCU board was 5.5 watts or 7.5 watts, depending on the neural network. This is not ideal. Ideally, the power consumption should be like the HLS approach, which is 1.5 watts, 1.75. But for the HLS approach, since we took more of, we didn't explore parallelism to its, we didn't explore much parallelism. We got very small designs and only obtained a speed up for the smaller neural networks. Compared to the other state of the art, we are so the other works are other use cases from the survey that we conducted that were performed some kind of space science and implemented them in FPGA when we have comparable results. So just to conclude, the most common neural networks in space are CNNs used for classification and are trained offline in a supervised manner. And then we, in our work, accelerated 4 use cases that come from ASAP, which included the VI encoder, CNET plus color, and the Sparta, and the MMS neural networks. Thank you.
Questions?
Perhaps.
Okay, go ahead. What are your next steps? Are you going to try different models that are more cutting edge, or are you going to try to reduce the size? Or
right now we're building our own accelerator, our custom accelerator. Follows ideas of a little bit of ideas of VT's AI, but we're trying. We'll see performs.
You had a question? Yeah. You also had a question?
Yes.
Yeah.
So in the table that you show, it's displayed. So there one column is about the whole board with the peripherals, right? So it's a big energy consumption, and then the next one is only the chip, right?
Yeah. So this column here is the peripheral of the board with the CPU, Ethernet MAC, all the peripherals on board. So this measures the 12-volt line. And this one measures just the power line in the connected to the FPGA chip, or the MTSUB, which
So in the end, we can advertise that our models are in the regime of 5 to 7 watts,
And even less, right?
or even less. That's they are going to the highest.
Yeah, with our custom accelerator, we are targeting the 2 watts.
Any other questions? Yeah. Okay. Then my question is, how do I interpret this energy per inference versus the PMPSOC?
Right. Energy per inference is so we execute inference 1 image at a time.
Yeah.
We don't do batch inferences.
Yeah.
So it's just the power consumption times the inference time.
Okay. Yeah.
Okay.
And you can see that it's
Okay.
better. It's 100 times better than the CPU executing for the variation autoencoder.
Yeah, that makes sense. Even CPU, GPU, there is a massive gap, right?
Yeah.
And you're even better than commercial GPUs in terms of energy consumption.
Yeah, in terms of energy consumption, for sure.
Yeah.
In terms of inference time, probably not. Commercial GPUs are probably better. But I'm not sure. I didn't run it.
All right.
Is this an average energy, or you have peaks that can be higher than that?
I don't have the graphs here, but this is maximum power consumption during inference.
Okay.
So the average is lower.
The average is lower.
So to speak, yeah.
But the graphs are very there. You could even trace 2 lines of the maximum and the minimum. There. Questions online?
Yeah, just one more question. So would it be difficult to try GMMs on FPGAs?
Good question. I don't know how the GMM algorithm is.
It's like, yeah, I mean,
I tried looking when
Yeah.
Vicky was giving her presentation.
okay.
I was trying to look
Maybe
it up.
this have to consider, right?
No, I think if you look for it, you will find it probably. Like somebody has done it.
Okay.
Yeah, but indeed, in the scope of this project until now, we have been mostly neural network oriented.
Yeah,
So
yeah.
it
I
would be
think it's
interesting actually to, if we have the time, just see if one traditional machine learning algorithm could also be included.
someone has even done Hermite polynomials on FPGAs.
Okay.
So it's
If it's vector multiplication or matrix multiplication, you can try. I think.
All right. Great.
yeah, very interesting.
Awesome. Thank you.
Thanks.